Hello, calculus. This is the lesson on limits at infinity and asymptotes. For us, this lesson is going to have a lot of similar features to a lesson we had way back in Unit 1 when we talked about horizontal and vertical asymptotes and evaluating infinite limits. This is just a more advanced version where we're going to get into some more complicated functions. So a limit at infinity is defined in notation here at the top of the notes, where the function has a limit, a constant value that it approaches as x approaches either positive infinity or negative infinity. We call that limit, when we write it as equation y equals L, a horizontal asymptote of the function. We've seen this and we've asked about this before. Although a function cannot cross the vertical asymptote, it can cross a horizontal asymptote an infinite number of times, so long as it's also approaching that value as x gets increasingly large. So the example provided by the textbook, I think, is a beautiful visual representation. You can see the vertical asymptote at 0, it's not crossing, and the horizontal asymptote at 1, it's going to continue crossing to infinity. Now we have 3 examples of computing limits at infinity, and we are going to be using our limit notation. So I'm going to switch to a pen. For the first function, the limit as x approaches infinity of 5 minus 2 over x squared can be broken apart using the limit laws. So we can do the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2x squared. And so we should be familiar with the rational function 2x squared. It has horizontal asymptote at 0. And so basically we have the limit 5 minus the limit 0, and the overall limit is 5. For our next example, we have f of x equals sine x over x, and we are going to apply a little squeeze to this. We haven't talked about the squeeze theorem in a while. So sine x is a sinusoidal function that is bounded by the values negative x and 1. So sine x over x is bounded by negative 1 over x. We're essentially dividing all sides of the equation by x. And then the limit also follows the same boundary. This is going to take a minute to write. And so rational functions, we should be familiar with the basic rational function 1 over x as well as 1 over x squared. And we know that the limit as x approaches infinity of 1 over x is 0, even when you make it negative with a constant. So basically, by squeeze, we know that the limit as x approaches infinity of sine x over x is 0. Then we get into the more complicated example, even more complicated than squeeze, and that is the inverse tangent function. And so in order to do this, I like to think about the tangent function first. And so if you're looking at a graph, inverse tangent is only defined from negative pi halves to positive pi halves, so that it follows the vertical and horizontal line tests, and it kind of looks like that. So those are our limits on tangent. And then there's an asymptote here and an asymptote here. Now inverses are kind of interesting because looking at this, the limit as x approaches pi halves of tan x is equal to, following the curve of the graph, infinity. If we apply inverse functions and we switch our input and our output, it goes to show that the limit as x approaches infinity of inverse tan x should be pi halves. But you can always check this with a graphing calculator and just graph the inverse tangent function and watch as it's bounded above. So these are all evaluated for positive infinity, but you could repeat each example and find the limit as x approaches negative infinity, following all of the same logic. Okay. So infinite limits at infinity is something that we've already done. We practiced the epsilon delta definition of a limit and proofs using that, including going to infinity before. So if you read your textbook, you can revisit those limit proofs from above. Just know that this notation is associated with the vocab infinite limit at infinity. So it's a limit at infinity because x approaches infinity, and it's an infinite limit because the limit is infinite. For the next portion, we're going to be talking about function sketching. And so we want to review from our previous algebra classes end behavior. So the end behavior of a function is literally what the function does at its ends. It can approach a horizontal asymptote, it can approach positive or negative infinity, and technically it could do neither. So like sine doesn't do either of those things as x approaches infinity. One relationship you should have memorized, but is included in this notes presentation, is that an even function has positive end behavior if it's positive, and negative end behavior if the leading coefficient is negative. Even would be x squared, x to the fourth, x to the sixth, anything where the leading exponent, highest degree, is even. For odds, the end behaviors are opposing. So an odd positive is going to approach positive infinity at infinity and negative infinity at negative infinity. And a negative odd function is going to do the exact opposite. So know these shapes, be comfortable with these relationships. Then we get into a review of rational functions and their end behaviors. And so this portion I'm actually going to divide into a second video so that I don't exceed my 15-minute limit.